Hi, this is for 530.204.1 Electronics and Instrumentation. I'm Dasgupta.
And I'm JHU ME, and we will be explaining how our circuit works.
Sweet. Hello, I'm here to explain the charging circuit for everyone. So the objectives of the circuit is to charge our capacitor to full 5 volts and not to drive it beyond its peak, and to tell it to stop charging when it is full. Now, as you can see, we first start off with the solar panel. Solar panel, by the way, is represented by our plus VS's throughout the circuit. Now, first we have power from the solar panel coming in, which feeds this voltage right here to this transistor, which turns it on, which then allows voltage to come through and start charging our capacitor. So it slowly starts charging from 0. Once it goes through, it meets the voltage divider, which is done by two identical resistors. So once it's halved, it feeds in through this wire, which goes all the way to this op-amp over here. And that value is the plus input for the op-amp. And as you can see, we have the other part of this where it comes through a plus VS, a resistor, and a Zener diode. Once this value reaches 2.5, it allows flow through this op-amp. Once the flow is available, it turns on this transistor, which then therefore tells this transistor to turn off. Once this is off, it stops flow to the capacitor. Since this is a voltage divider, we assume that the voltage at the capacitor is 5, since we get a flow of 2.5. Once we get a flow of 2.5, we just allow flow straight from the capacitor down to the rest of our circuit. And thus, the capacitor is never driven beyond 5 volts, and once it reaches 5 volts, the charging is stopped.
And that's the charging circuit.
Sweet.
Hi, so I will be explaining the illumination circuit, and the objective of this circuit is to have an LED turn on when it's nighttime or the light's off, and turn it off when it is daytime and the light is on. So this LED is supposed to be supplied with a constant voltage and current from this current amplifier. So to start off explaining this, this current amplifier should output a constant voltage and current. This is achieved by giving it a constant voltage from this reverse bias Zener diode, which should give the op-amp right here a constant voltage of 0.6 volts. And the current amplifier, using the potentiometer and the voltage divider will output a constant voltage as well as a constant current. And this can be changed by this potentiometer right here, which will later on control the overall intensity output of this LED. So once this has a constant voltage and constant current, it will go to this diff switch, which when we turn on will allow current and voltage to flow through, but when we turn it off, it will turn this circuit off and not output anything. And so when the switch is turned on, it will give this PNP transistor this constant voltage and constant current, and this PNP transistor is turned on when this voltage source of the solar panel outputs a low, so when the light is off. And when it's on, this will give the PNP transistor a high base input, and this will turn the PNP transistor off. And this will, when this solar panel is off, it will turn this transistor on and allow current and voltage to flow through into the LED, thus turning it on, and that's our illumination circuit. So now I will be explaining the charge monitoring circuit, which is a circuit that has to have two LEDs which monitor the amount of voltage that the capacitor has charged. And when the capacitor is over 4 volts, it is supposed to blink one LED, and when it is under 4 volts, then it will charge the other LED. And so this circuit these LEDs they need to blink 0.1 seconds for every 2 seconds they're off. And this is all from the timer circuit, which after we calculated the capacitor and resistor values, we could output a high of 2 seconds and a low of 0.1 seconds, which is the opposite of what we need, so we reversed it by having it go through a PNP transistor. And so when this timer chip outputs a high, then this will turn this transistor off, and when this timer chip outputs a low, it will turn this transistor on, thus reversing the output. And so when this voltage from the capacitor goes through here, and this transistor is on from the timer chip for 0.1 seconds, it will allow the voltage and current to flow through here to these LEDs. And these LEDs are turned on because over here we have two comparators, both powered by the capacitor, and one input for each one is a voltage divider from the capacitor. And this voltage divider is calculated so that when the voltage of the capacitor is 4 volts, it will output a voltage of 0.6 volts. And this other input is from the reversed by a Zener diode, which will output a voltage of 0.6 volts. And so when the and both comparators have the same inputs except on different terminals. This one has the voltage from the voltage divider as the plus input, and this one has it as the minus input. And so one of these will always be outputting a high, and the other one will always be outputting a low. And so when the other one outputting a low, this will cause a potential difference between the output of this transistor and the output of the comparator, which will then turn on the LED. And as for the other comparator, when this outputs a high, and this is a high, there's a small voltage difference, thus not turning on the LED. And then when they're reversed and the other input is higher than the other input, then the LEDs will be switched. The voltage outputs of the comparators will be switched, and it will turn on the other LED. And this is our charge monitoring circuit. Ready? So now I will be explaining the flashing beacon circuit. The objective of this circuit is to have an LED turn on when it is nighttime and turn it off when it's daytime. This LED needs to be supplied with a constant voltage and current, as well as be on for 0.1 seconds for every 1 second. So to start off, this timer chip outputs a high when it is outputs a high for 1 second and outputs a low for 0.1 seconds. This is achieved by calculating for these capacitor and resistor values and using an equation to do this. And this output is reversed by this PNP transistor. So that when this outputs a high, then this turns this transistor off, and when this outputs a low, it turns the transistor off. This was all mentioned earlier in the charge monitoring circuit. And so, similar to the illumination circuit, this is the emitter of this PNP transistor is supplied with a constant voltage and current from this current amplifier. This current amplifier can be adjusted by the potentiometer right here, which later on affects the intensity output of the LED. And so when this transistor is on and this is outputting a low, the voltage and current is allowed to flow to this PNP transistor, which again, similar to the illumination circuit, the base is supplied from the voltage of the solar panel. So when the solar panel is outputting a low, it will turn the transistor on, and when the voltage of the solar panel is high, it will turn this transistor off. And when this is off, and this transistor is off as well, and the voltage and current will flow through to the LED and turn on the LED. And this circuit is basically a combination of the past circuits, and that's our flashing beacon circuit. So this is our circuit, and here's our lamp. This represents the sun. Here's the solar panel, and this is our circuit. This is the multimeter, which we will be using to measure the voltage in the capacitor. And first we'll be demonstrating the charging circuit, which should charge the capacitor to 5 volts. And so we will turn on the power source, and as you can see, the voltage of within the capacitor, it's charging right now, and it should stop at 5 volts. This is the LEDs are the capacitor is still charging, and it's at about 2.6 volts right now. And these LEDs are from the Illumination Circuit, which are supposed to this LED is supposed to light up when it is below 4 volts, and this LED is supposed to light up when it's over 4 volts. So since it's under 4 volts right now, this LED is flashing 0.1 seconds every 2 seconds. And so right now our circuit's working correctly, and we'll wait a little bit more. Okay. Start taping.
Yeah.
All right, so as you can see, this LED is still flashing, and now that it's reaching 4 volts, it should start switching. And
Green flashes.
so now the green is flashing, which means that it's over 4 volts, and our LED is still working, or our circuit's still working correctly. And it's at about 4.3 volts, and so in about 0.7 volts, this capacitor should stop charging. No, wait, no, not yet. Why did it stop?
Yeah. It's up.
So now the voltage of the capacitor has reached about 5.06. It has been there for a little bit now, and as you can see, this is our voltage divider, right? Or this is our Zener diode, which is supplying the op amp with a constant 2.52 volts, and this is the voltage of the voltage divider, which is supplying with a 2.53 volts. And since that voltage is higher than the voltage of the Zener diode, it should be, and then that is turning off these two transistors, and thus allowing this turning off the charging of the capacitor, which is still at 5.06 volts. And our lights from the Illumination Circuit are still working. This is flashing because it's over 4 volts. And now we will demonstrate the Illumination Circuit.
Yeah.
So for the Illumination Circuit, this LED should turn on when we turn off the voltage source. And as you can see, the LED does in fact turn on when we turn it off, and it does turn off when we turn on the voltage source. This could be adjusted by this potentiometer right here, which will control the overall intensity of the LED. And this can also, this dip switch right here, this will turn on the circuit. And that's our Illumination Circuit.